Hey, Dilakshi.
Hi.
What's up with the dinner? Done with the dinner?
Yeah, we came like half an hour before.
Okay, okay.
So only two of us are here, no? Still?
Yeah, I think everyone forgot.
No, maybe 3 minutes more, no? They are waiting for the time. It's
So,
punctual.
oh, very punctual, huh?
Yeah.
So did professor ask us to turn on the cameras or we can keep it off?
He prefers if we can.
Hmm.
Something like that he told, no?
Okay, okay.
Yeah. If Ravina is coming.
Hmm.
Are you done with the homework? You finished?
Homework? No, I haven't started.
Homework. Sorry, I missed it. Not the homework. The mid.
Oh, the mid. No, no, not yet. I have to finish one question. The diagram, I haven't done
Ah,
it.
yeah.
अच्छा, समोसे फ्राई कर लेंगे आप? मेरी क्लास है, ये फिश फ्राई कर दिया मैंने, आजा। हाँ, उनको बुला ले यार, ये माइक ऑफ कर।
Hello.
Oh, guys.
Hello.
Nice. Can all of us hear each other?
Yeah, I can hear you.
Okay.
Yes, I can hear you. Hi, Professor.
Nice. Okay. Hi, Abdullah. Hi, Ryan. And Dilakshi and Pravina.
Yeah.
Okay.
Yeah.
Nice.
Okay.
Yeah. Yeah, it helps to have video, but no big deal if you don't want to open it up. No. Hey, Aryan.
Hello. Can you hear me?
Yes, I
Yeah.
can. Ah, you have Maz here. And I think I have a camera, better camera. Hello, Maz?
Yeah.
Hello.
Okay, give me a second. I might be frozen for a minute. Okay, am I unfrozen? I think whenever I put my camera on, I freeze. Okay. Let's see. Okay, is this audible, visible, everything?
Yeah.
Yeah.
And we are someone, right? 1, 2, 3, 4, 5, 6, 7. We need Manuka too. Yeah, he's always here. We'll give it a minute or two because it's a new setup.
I think somebody's audio is what's it called? It's echoing.
Is that echoing? Is it me?
No, well, possibly. I don't know though.
Let's see.
I can mute mine, see if
Now it seems okay. I think.
I muted and it got okay. Hello?
It sounds okay, yeah.
I think now it's okay, right?
Yeah,
I think it was someone else's,
That's it.
maybe.
Okay. Yeah, let's give it a minute. Or Manuka, here is. Hey, Manuka, you managed to get late even for an online one.
Yeah.
Okay, nice. Okay, that's nice. We can have a online class in a relaxed manner. Okay. So have you guys cooked for tomorrow?
Yep.
Yeah,
Huh?
yeah, think so.
Oh, nice.
Bringing a Persian dish, so.
Persian dish. Okay, nice, nice.
I'll cook in the morning.
Cool. Pakistani. What do you plan to?
Yeah.
Do you have any plan?
Maybe biryani.
Oh, nice. Fantastic. Okay. Cool. Okay. So let's do this. Anything particularly you want to point out? How was the midterm?
Pretty decent.
Okay.
Yeah, it's pretty good. Do you want us to all show the quiz here?
Oh yes, yeah. Show up here your quiz, each one of you, so that I can go and zoom in and see. Okay, there you go. Ryan, I can see. Good way of submissions, right? And I just have to look into the recording. Yeah.
That good?
Yes, that was good, Ryan. Yeah. What about others? No one else? Oh, no quizzes. Okay. So no one else has a quiz to submit? Okay, Ryan, maybe you can take back your quiz and so that others don't lose points.
Yeah.
It's
Okay.
kind of hard to see in the lighting, though.
Okay. Nice. Okay. Okay, only two of you. Okay. That's okay. I think I'll be dropping quizzes, so some zeros are fine. Is that fine? Okay.
Yeah.
Yeah.
Okay.
Yeah. If you're seeing me on a gallery view, I think I might be tiny. When I write on the board, you can pin me. I think probably you guys know how to do this, right? You can pin my video and the screen will get bigger. Is that clear what I mean, all of you guys?
Oh, yeah.
Okay. Okay. And thank you again for coming. And let's see. So we want to do electromagnetic scattering. Or before that, I should make some announcements, right? So we are going to have the final exam. I haven't yet made the final exam, probably tomorrow or day after tomorrow, right? So that's how it should show up. Meanwhile, you guys have your homework to work on, right? So, but
Oh, yeah, I think I have a quick question.
Yes, please.
I think I noticed in a mistake in the homework 13.
Okay, go ahead. Tell me.
I think you wrote down J of RW or R omega, when I believe you meant to say J of K omega.
Oh, possible. Okay, which equation is this? Let me change the camera again. Let me see.
I can actually share my screen potentially.
Yeah, that's better. Yeah, that's easier. Good. Some advantages of online things.
Do you guys see it?
Hold on, let me expand this so that I can read. Yeah, okay. Which equation? Yes.
I believe right here. This should be K omega, right?
Let me see.
Do you see it?
Yeah, I see it. I see it. I see it.
Oh, okay.
Yeah, I'm just thinking. Give me a second.
Oh, okay.
Yes, that's right. Yeah, K of omega. Yeah, that's a final.
Okay.
Yeah,
Okay, and these remain R omega,
that
right?
remains R. Yeah, correct.
Okay, cool.
Yeah.
That was it, I think.
And K itself is very funny. K is omega over C times R hat.
Mhm.
Even though it has dimensions of K, but it is basically, again, in the direction of R hat. It has a direction of position, but the dimensions of K, 1 over position.
Yeah, okay. I think that's it.
Okay, good. Yeah. So that's good for others too while they're working on it. Yeah. Thank you, Mass, for pointing out. Yeah. So you guys have started on the homework. That's good. Okay.
Yeah.
Yeah, good. Okay. So okay, let's see. Yeah, the final exam will be take home, which will be uploaded anytime in the next, let's say by Wednesday at the most, hopefully by tomorrow. And there will be 1 or 2 questions, tiny final exam on Friday. Something very straightforward, almost like dimensions and dimensional analysis. At least 1 question, I was thinking about it today, might be dimensional analysis. And yeah. Okay, so we want to do
Okay.
electromagnetic scattering. Is this readable?
Yep.
Yes.
And like the usual class, feel free to ask questions, interrupt me anytime. So this is almost okay. So what we have had till now is that or whatever we did in radiation. So that is radiation that we have studied. And any one of you want to summarize what radiation is? If you have to explain it to an undergraduate student, let's say, introductory physics or somewhere, how would you explain radiation? Summary in 2 sentences.
Radiation is the oscillatory motion of the electric and magnetic fields, oscillating in time and position, overall space.
What causes radiation? Yeah, that's good.
When the observer's point is greater than the source distance from the origin.
Yeah, that's the approximation in which you get it. But overall, what causes radiation? Maybe I should ask. How would you generate radiation? If I change my question a little bit.
Moving charge.
Moving charge and specifically accelerating charge.
Yeah.
Correct. So
Yeah.
you need acceleration. If you just have movement, it doesn't cause radiation. So accelerating, so radiation is sort of generated by accelerating charge. Correct. And so there are 2 things here. First of all, we need a charge and it has to be accelerating. Acceleration is easily generated by oscillating. Like when you oscillate, there is an acceleration, correct? Or when you're going in a circle, that's also, you have an acceleration, correct? Circular motion implicitly requires acceleration, which is towards the center of the circle. So you would like to have the charges to accelerate, which this seems very tricky because most of the atoms are neutral. Like, so when we are talking about materials, so materials are neutral. But so that means, that doesn't mean that materials do not let's say radiate. What you would think of is that if you have an atom, So this is a neutral atom. They can have a dipole moment, not necessarily a permanent dipole moment. You can induce a dipole moment, right? You have a positive and a negative charge. And the dipole moment could be accelerating. Right? So we talked about if you have an accelerating dipole, that means a second derivative of the dipole moment. So a neutral material can be polarized. You generate a dipole moment that radiates. So this radiates. In fact, there is another way of generating radiation. That could be, you could induce a magnetic dipole moment and again make it change, and this radiates. Okay, so there are two ways of generating radiation. Either you induce in a neutral material, either you induce an electric dipole or a magnetic dipole and then make it oscillate. Right, so that's the idea of accelerating charge in the context of neutral materials, correct? And we will not have in this whole discussion, just for making it simple, we will not talk about magnetic polarization at all. We will only talk about electric polarization. Simple thing is that it is simpler. And so our electromagnetic scattering then is, you have a material here. We know that if there is an accelerating charge, it radiates. But now we want to have this neutral. So what you do is you make it go with an induced electric field. So you send light in here. So a monochromatic wave, let's say, that's an incident monochromatic wave. That is an electric and magnetic field. It's like light, you have electric field and magnetic field perpendicular to each other. Remember, you have, that's your wave and that's your crossed wave, right? So if that makes sense, like that's perpendicular to each other, you have electric and magnetic field. This will polarize a neutral material. This polarization will oscillate under this electric field. Because the electric field is oscillating, the polarization will oscillate. That generates this acceleration, and this will radiate. So there is R prime here, and then there is observation point. So we have been talking about radiation alone, like if there is an acceleration, there is radiation. But now we are saying that that acceleration is induced by an incident electric field or incident magnetic field, which is oscillating. Is that clear, the theme that we're talking about? Incident field, and that's the radiated field. We want to write equations for this. So broadly, what we will talk about is, so let me write down what we mean by that. So that's, let's say, so to include the incident and the radiation field, we of course have Maxwell's equations, but now we want to write it in frequency domain. So Maxwell's equation, and what is the source? We are talking about induced polarization. So Maxwell's equation, remember, is gradient dotted with epsilon naught electric field. Let me write it in the frequency space. So that's R omega, and that's equal to rho of R omega plus. If there are dipoles, I will say this is induced polarization. That's your P of R omega. These are polarization. Is that a familiar idea? So usually we do not have this, like, or at least I have not been using that significantly. What we're talking about is that if you have a neutral material, so if this is for charges, if I have a material where I have negative and positive charges, so they will all polarize in the presence of an electric field. Right? They tend to polarize negative, positive. So let me say this is negative, positive, negative, positive. In general, they're all random. You put in an electric field, they try to align with it. They mostly rotate themselves to that, to the induced electric field. And this polarization depends on the induced electric field. So let me write that as an expression. Let me erase this so I don't have space. So this P here is equal to chi, that is a susceptibility, or omega dotted with electric field. And that is an epsilon naught for dimensional reasons. Okay. Now this seems very algebraic, correct? So you multiply the susceptibility with respect to electric field and you get P. That's very misleading. That's because we are in the frequency domain. If you are in the time domain, this actually looks like T is equal to time integral. So remember, all these atoms are trying to polarize or align themselves along the electric field, and that's equal to our T minus T prime dotted with epsilon electric field in the time domain. And we are saying that all the times contribute to that. And what is wrong with this expression? Anyone?
Isn't the electric field supposed to have a T prime in it?
Good. That is correct. That is a mistake, but that's an error on my part. But even now there is an error. Thank you. That's a good point.
Dyadic.
Dyadic. This is a dyadic. Yes. This is This is a vector. That's a dyadic, and you get a vector. So that seems okay. But there's a very big conceptual error in this. So remember again what we are doing. We have a negative, let's say there's only one polarization, correct? That's your dipole moment, which is captured in this. And now I put an electric field in here, which is a time dependent quantity. And this polarizes, right? It was neutral, it polarizes this. And that polarization is given, the polarization at time t is given in terms of the electric field at time t prime. Can you see anything wrong in that statement that I spelled out? The polarization at time t is given in terms of the electric field at t prime, where t prime goes from minus infinity to plus infinity.
It seems like there's two Fourier transformations there.
It seems like what?
Like two Fourier transform, like it's going from frequency domain to time domain, right? Both of the.
On the top, yes, but here at the bottom, it's time, right? This is time. This is time. That's time. So I'm not really going into like, this is what I would like to motivate, but I'm saying there is a mistake in this line. There's a fundamental mistake. Huh?
In the second line?
In this line, yes. So let me repeat again, think carefully listen to my words, the polarization at time t in the present depends on the electric field at time t prime, where t prime goes from minus infinity to plus infinity.
Oh, is it causality?
Oh, so,
Very good, right?
oh,
Minus
yeah.
infinity is
The
past,
past.
plus infinity is in the future. Future cannot affect my present.
Mhm.
So I have to get rid of the if it is causal, I have to get rid of the future affecting the present. So by hand, just by hand, I have to get rid of that and say that this is t. No future can affect my present. Present has to be only affected by the past. That's causality, right? And that plays a very crucial role in going from here to here, right? So it is a product, but now where is the causality in this? Like now I am in frequency domain. Where is my causality in there? And the causality shows up, and I'm not going to show that here. This usually we do it in the first semester of the course. So this is just a statement which you will need in the next week's final exam. This is a concept that you will need. This is in the time domain. The causality has to do with t being greater than t prime, right? That's causality. How does this show up in the frequency domain? Frequency domain doesn't have any integration. There is a susceptibility, which is basically a dielectric constant, which decides how much it will polarize. But just by going into frequency domain, this is complex now. Like susceptibility is no more real, it is complex by construction. And the real part of chi and imaginary part of chi are related. And that's called the Kramer's chronic relation. That's a jargon. I did not give you much information. I just told you that there is a complex part, where there is a real and imaginary part, and I said that they're related, correct? But more intuitively, real part of chi, this is your reflection coefficient or refractive index. Right, that decides how much reflection atom happens in a material. Okay, so if not for polarizations, you cannot think of reflections. Okay, all this reflection and absorption basically is a light coming in, it is oscillating the material, and it is radiating again. Okay.
Okay. So this is in linear susceptibility.
Yes,
Term.
good point. When I say that polarization is some constant times the electric field, I have assumed that these are all linear. Correct. Good point.
And that's part of the,
Part of
where
it.
refraction and the real and imaginary are
Mhm.
good.
Yeah.
Okay.
Like there will be corrections to this if you were to assume that there are higher orders. Yeah, good point. But most of the time it is sufficient to work in linear. I mean, most of the there's physics is already very, very rich, and there is a lot of issues we have already with linear. So let's stick to that here at least. Yeah, but be prepared to go out of that linearity anytime. But my point was that the causality shows up in the fact that refractive index and the imaginary part has to do with absorption coefficients. Absorption coefficient has to do with if you shine light on a material, some of it reflects and some of it gets absorbed. Correct? Now, here is the interesting part. If someone tells you that there is a material which reflects all light, zero absorption, that's impossible. Because of Kramer's conic relation, these two are related. If absorption coefficient is zero, reflection coefficient has to be zero.
Even mirrors?
Even mirrors, there is always an absorption coefficient. Okay, so otherwise we are violating causality. Okay, so very
Okay.
non-trivial.
All right.
Okay, so in fact, most of the time, absorption coefficients are not even measured. You measure the reflection coefficient and use this Kramer's conic relation to mathematically derive your absorption coefficient. Of course, that's not always true. Often you measure the absorption coefficients too, but it's interesting that it is so, I mean, causality is so much respected, if you want, that you even derive that from the reflection coefficient. Remember, all these are complex quantities. So we are talking about frequency dependent quantities. This is a refractive index, frequency, color, right? Refraction, did we lose someone? Something happened? No? Okay, yeah, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we're all there. Yeah, I think. Yeah. Suddenly
Still
there
here.
was a change on my screen. So okay, so my point is that refractive index is a frequency dependent quantity. That means it's color dependent, whether it's red light, green light, or blue light. Refractive index changes, light behaves differently. So that's what we are meaning here. Okay, so now suddenly earlier we were talking in terms of charge and current. Now we are saying that we don't want to have charge. We're talking about neutral materials. There is no charge. There is polarization. In fact, we will have polarizations that are induced by the electric field. So the induced electric field is here. So this is your source. Okay. So the dielectric function of a material. What is chi? Just I should point out chi. Well, that's a susceptibility, right? What is chi? Anyone? In terms of dielectric functions, so that's epsilon,
So,
right? -1, right? And in fact, for dimensional reason, you just divide out by epsilon. Now, is that a familiar idea? That's a dielectric permeability or dielectric permittivity of a material relative to vacuum. Familiar with me?
I
No.
think it's written a little differently.
Okay, so maybe I'll derive that in a minute quickly. Okay, let's see. I think I motivated it, how causality comes in, but now let's say this is what it is. Put this on the other side, and what we have is del dotted with epsilon naught E, correct? And del dot P is nothing but chi minus of epsilon naught E. So it is plus chi dotted with epsilon naught E is equal to rho, if you want. Let me write that again in the frequency domain. That's your rho. But this is what we say is D. Correct?
Yeah. Yep.
Which we say is epsilon dotted with E. So write that down explicitly. Epsilon dotted with E is equal to epsilon naught times E plus chi dotted with epsilon naught times E. electric field is there all throughout. So what I have is epsilon is equal to epsilon naught plus epsilon naught chi. That's a relation between the dielectric permittivity and chi, or the susceptibility, and divide out by epsilon naught. So this implies that chi is equal to epsilon over epsilon minus 1. This is dielectric permittivity of the material, and that is electric susceptibility. Good. Okay.
Okay, yeah.
So
See,
that's your first Maxwell's equation. And I want to, let me go to the other board. So overall, what we have is that whole set of equation can be thought of as divergence of displacement field is equal to rho of r omega, where d of r omega is equal to epsilon. And let me also make the approximation that in general anisotropy is good. Let me make it all isotropic so that there is no dyadic nature to that. It is just isotropic. It is diagonal in that, and it is just multiplied by an identity. That's just simplification again, but it's very easily generalizable in the formalism that I will give. We can put that as a dyadic, and it will extend almost immediately. Okay, so that's your first Maxwell's equation. The second Maxwell's equation is the same thing for the magnetic field, and that's this. What is that equal to? What's the right hand side?
0.
0. Good, right? So that's, and this is the magnetic permeability, but I'm going to simplify again. That's going to be mu naught, no magnetic permeability. Okay? And it is a little harder, more work to include the magnetic permeability, just because it comes up in the inverse form. Little more work, tedious, but we won't even attempt on it here. Okay, so that's just for your information. There are two more equations. That's del cross electric field, or omega is equal. Remember, we are in frequency space. This is not time derivative. Remember, in frequency space, time derivatives can be replaced with minus I omega. Right? So this becomes plus I omega times b of r omega. And the fourth equation is in terms of h. H is here. It's almost b except for mu naught, and that's equal to, this becomes I omega, that is a d, and plus j, the current. Okay, that should be sufficiently motivating or intuitively clear. The same charges, it's in the frequency space, time derivatives got into this, and the significant change is in the d, because I have a material now. D has its material properties in here. And that's important because this is going to be our scattering material. Like this is when you think of scattering of light from a material or reflection or refraction that is happening, that's that material property. Right? That's the reflection and absorption coefficient is inside in here. Right? Chi is having reflection and absorption coefficient inside in here. In general, of course, we have charges and currents. We are interested in neutral materials. So we are going to consider situations where they don't exist at all. We don't want them. Okay? In that case, if you take this equation and take a divergence of this equation, what is the left-hand side? What is the divergence of a curve? Divergence of a curve?
0.
0.
It is 0. Very good, right? Divergence of a curl is 0. Immediately means divergence of the magnetic field is 0. That means this equation is no more independent. This is inside in here. Right? If this is true, and if there is no charge or current, this is implied by this. So I don't need that equation at all. So this implies this. Same thing in here. I take the divergence again. I get divergence of D equal to 0. This implies this. So I have only two Maxwell's equations. So Maxwell's equations now are that del cross E in the frequency domain is equal to I omega B, and del cross H, everything is in position and frequency, is equal to minus I omega D, where D is equal to epsilon times E, and magnetic field is equal to, I'm keeping no magnetic material, so that's just this. Okay. So these two equations are sufficient when you're doing optics. We are pretty much doing optics, but we're doing mostly, we are going to do it in the radiation zone where the observation point is very far away. And so we won't call it optics. Instead, we will call it electromagnetic scattering. But the formalism goes through optics if we do not do the radiation zone approximation. So this is an extreme scenario of optics. Okay, with me?
Why did we choose rho and J are equal to 0?
Just because we want to work with neutral materials.
Because neutral is
Neutral means, for example, I want to talk about electromagnetic scattering of a molecule of nitrogen in air. There are no free charges. It's all induced charges. I can induce them here and there, but there is no free charges. Is that clear?
Yes.
Manuka, you had a question? Just ask me questions.
Yeah.
Because I really don't go see the hands and all. So just ask.
Yeah.
Yeah.
So in the D equation, how does the dyadic goes away from the epsilon?
There is a dyadic. So this is the complete expression. Right, but
And the dot between-
I'm simplifying saying that the whole dyadic is a constant times 1. Right, so this is an approximation. I'm thinking of a material which is isotropic. So when you think of a material, you think of refractive materials. I'm sending a light here and it gets refracted. Now, if you rotate the material, does the refraction coefficient change? So usually there are 3 reflection coefficients depending on in which direction the light is going. Like electric field in the X direction polarizes in the X direction. Electric field in the Y direction can also polarize in the X direction. Not very common, but they are called birefringent materials. In optics, there is a lot of interesting materials you can think of. But I'm saying I want to work with very simple materials, let's say isotropic material like glass, like simple glass in whichever direction you look at, it's all the same, like simple crystals. Okay. So,
Okay.
but very easily this whole formalism can be extended to that case to a certain extent. Yeah. As far as,
Okay.
especially for the radiation zone, it can be easily extended. Okay.
Okay, thank you.
Yeah. Okay. Okay, so that's our equations. Now Maxwell's equations are pretty simple now. Now we need to have our radiation zone, correct? Yeah, maybe I'll make a simplification right here. Yeah, okay. So radiation zone. Okay. Yeah. So again, rewriting that here. So make it small. L cross E. It's all in one side. I'll write the position and frequency, right? I omega B, same thing. And del cross H is equal to minus I omega D. But we are having our situation or a model as there is an electromagnetic wave coming in, which is incident electric field, and there is an incident magnetic field, which satisfies monochromatic wave. Let's say they are perpendicular to each other and R is going straight perpendicular to that. Again, that's an approximation. In general, true for any incident pulse if you want. And there is radiation that happens in this direction, correct? That is E, that everywhere around. So how do you want to capture that electric field? So that's given by what we will call, remember, any differential equation is decided by the boundary conditions also. So the boundary conditions in here, this is called the Sommerfeld boundary condition. Just a boundary condition basically, but captures the main idea of electromagnetic clearly. There is a total electric field. That's your total electric field. Let's make it frequency domain. It consists of two pieces. One is the incident electric field. And leave some space here because I'm going to add on some feature in here. Plus, there is a radiation component. So there is something that is incidentally coming, changing the or inducing or oscillating this material, all the atoms in the material. It induces a dipole moment, makes it oscillate, and it radiates. And that radiation we know has to obey the radiation condition. And that we will say is given by R hat crossed with R hat based on the radiation, whatever we learned in radiation. And that is jotted with some vector K. This is what we have to find. This is the unknown in the scattering. This will be called the scattering amplitude. This will be R hat and omega. What do I mean by R hat? R hat depends on theta and phi. It's on the dome. Like whenever it's on the dome, it's a solid angle. It depends on which angle you're in. And that is this exponential IKR over R, right? How far you are. This is that radiation approximation that 1 over R, when you square it, it cancels out the R squared. This information is primarily coming from what we learned in radiation, right? So we want that radiation zone, and this is the this is the unknown. So we want to write the solutions to this equation in this form and recognize this. This will be called, there is a vector associated with it. This is the vector scattering amplitude. R hat, so this is also, you can think of this as k theta phi omega if you want to think of it in terms of actual spherical coordinates. But let me keep it in a very generic so that it's a geometric quantity.
Is it vector?
It's a vector, correct. Usually in the standard simple literature, you're talking about usually scalar quantities. Remember, that's also a good point to clarify that most of optics and scattering was developed before Maxwell's equations. Like optics was done by Young, like Fresnel, Young. They were all, Fresnel was in 1810, 1820. There was a significant development made by Fresnel. They are usually called Fresnel's equation. Before that, all the law of reflection, law of refraction, that was known in 1500s probably, or 1600, like at the time of Newton, it was all there. It's very simple. Angle of incidence is equal to angle of reflection. But what we could do after Maxwell is that we could derive it. And most of what was done before Maxwell's equation was, we did it using scalar fields. There was a scalar wave and it reflected off. There was an understanding. We didn't know that it was an electromagnetic wave of electric and magnetic field, but broadly that's the laws were derived out of that. The only thing what we are doing here is that the law of reflection, which is a very straightforward relation, the angle of incidence is equal to angle of reflection. We can derive that using this, very tedious, but we can derive that angle of incidence is equal to angle of reflection. Very simple in fact. And by the way, maybe I should ask, I usually, I mean, it's always easy to ignore that. Is law of reflection unambiguously stated by saying that angle of reflection is equal to angle of angle of incidence is equal to angle of reflection, or do you have to say something more to it? Do you have to add something to that?
Depends.
Depends. Okay, clarify.
Depends, I guess. Potentially, what if it's like a photon, maybe, or
Let's keep it classical. So I mean, it's kind of a tricky question, but let me elaborate
I
on
think it
it.
should be in the same plane.
Oh, very good. Yeah. Yes, please.
I think it should be in the same plane as the incident and reflective.
Yes, that's correct. That's what I was intending. So notice that when we say that angle of incident has to be equal to angle of reflection, we say angle, this is theta I, theta R. But just by saying it is an angle, you can also have it come out of the board, right? But what we need is that the normal line, angle of incident and angle of reflection, they all have to be in the same coplanar. It's kind of a understood, but most of the time we are drawing the diagram in the plane of the board. So it's kind of implicitly in there. So sometimes it is good to recognize that fact. And those details sort of come in very clearly when you do all this derivation. But it really seems if you're not, see, there are two ways of looking at anything. You have a law and you can trust that law and proceed to apply the law, then this is pretty much too much work for just angle of incidence is equal to angle of reflection. But if you would like to know why that law is really true, getting the fundamentals of that equation, then this is how to proceed. The Maxwell's equation lets you derive the law of reflection and law of refraction. In fact, a little tedious. We won't be able to do that here. We don't have the time. But in principle, yes, if we had about a week or so more, then we could have actually derived that. It's a matter of doing the Green's function, deriving the Green's function, and it's a boundary condition that gives you the. Okay, reasonably doable with our current mathematical machinery that we have. Okay. We
Is
won't do that.
depends on the
Yes, please.
just R vector or just
Tell again.
E in the
Yeah.
incident.
Oh, that's a
It
vector.
depends on the
I meant to say
vector or the dependence of R
This is a vector, and this is also a vector.
vector.
Sorry.
Okay.
Right. Yeah. Does that clarify?
Yes.
Okay. Now, there's still a little bit different. So this boundary condition, that's not the complete story. A little bit more. I said you need to leave some space here. That's because radiation zone is in very far, right? You're on the dome, right? R is practically at infinity. So we're not interested in the total electric field. That's the main idea. So the condition is in the limit R tends to infinity. Okay, so this boundary condition is on this dome, right? R tends to infinity. Okay, just think of a dome there surrounding this tiny material, and it is starting from somewhere here. Incident beam goes straight, but this scatters off, and that's what shows up. And this is limit R tends to infinity again. So that means that this will not depend on R. The moment you take R tends to infinity, R information is gone, right? You're on infinity, so there is no R there. There is only angle, and there's only angular dependence in here, right? But that will have the information. It depends on this quantity in the sense that whatever happens here is decided by something very small. So R prime integration decides it, so the material decides that, but the scattering itself, or the scattering amplitude, is on the dome. Okay, clear? Is that construction of the problem clear? And the main question is, what is this? And we are going to get an expression for this quantity. Okay. So we started at 9, it's already 9:55, so it can take half an hour more. So advantage of not having a regular class is that I can go a little further, half an hour. Okay, and that way I can do it at a stretch and complete this in a sense. Then Thursday will be easier. Okay, so we want to find K, and that's our equation. These two equations, that's our simple equation with the boundary condition gives us, and our goal is to find K somewhere inside in there. Okay. Okay. This relates to your homework now. The homework that is due. Let's say we start from this equation. That's your statement of the problem. Start from this equation. Take a cross product. So cross product of the first equation. Everything is in position and frequency. When I take the cross product, I have to take the cross product on the right side also. So it's I omega. B naught is nothing but mu naught times del crossed with H. Right. But del crossed with H is nothing but minus I omega D. So I have I omega mu naught times minus I omega times epsilon times E. So the curl of E, this is not minus, by the way, this is a product, right? Is equal to some omega square times that epsilon. Okay. Multiply by an epsilon naught and divide by an epsilon naught and multiply by an epsilon naught. Notice that mu naught epsilon naught is c square. I and minus I goes away, so that's equal to omega square over c square. That's your frequency square coming in. Remember, square of frequency means in time second derivative of time. every frequency has to do with derivative, right? So all radiation zones will have this omega square sitting in here. That's a signature that it is a second derivative. It's an acceleration that is contributing to it. Okay, always look for that. And there is epsilon. Let me write this more explicitly, over epsilon naught times electric field. Again, I put in some space. If I had no source, there will be no scattering. The source is this dielectric permittivity. If there is no source, there should be no scattering, right? So let me remove that piece. So I'm going to subtract 1 and add that 1. That's plus omega square over c square times E. Is that clear why I did that? I just want to add, or in the case of no source, I should not have that piece. So this is the piece that is there in the absence of the source. Any questions there? Just that.
So you're just adding the electric field in
and
where there's no source.
and or think of this now that if epsilon was, if it was 1, right? Epsilon was epsilon naught. This was vacuum. This will cancel out. This will be 1. 1 minus 1. This is 0. So this whole thing is just source now.
Okay.
And in that case, it is just simply this. I could have done that here itself. In that case, it is just epsilon over epsilon naught. But then I can identify the susceptibility, and that kind of gives me the idea of a source more easily. Okay.
Okay.
The second
you.
term is for the vacuum, you said?
Okay. If it was a vacuum, this will be equal to 1, right? Epsilon naught over epsilon naught.
Yes.
That's that piece here, right? So whatever is remaining is the case when there is no vacuum, when that is different from vacuum. Okay. So, or maybe I should write the next line, then you'll get this better. Since there is no space, I want to erase this and get that space. Maybe, yeah, let's do it here. Delete this also. So my equation is now, so it's a dyadic equation crossed with electric field, or not yet a dyadic equation. Let's bring that down here. Electric field is equal to omega square over c square times chi times E. Is that clear? The advantage of writing this is, see, this looks probably simpler, but the advantage of writing this is right-hand side is your source, left-hand side is your effect, cause, effect. In differential equation, in homogeneous equation means there is nothing happening. Inhomogeneous equation gives me my effect. Right? The moment I set it to be 0 on the right side, there is no scattering.
Oops.
Right? If I need scattering, I need the right side.
There is no scattering, then it's just the source.
Then it's just the, or source is just vacuum then. So if it is vacuum, there is no scattering. Right? Chi
Okay.
is equal to 0 for vacuum. Is that clear?
Yes.
And that's our central equation plus the boundary condition. And whenever you have a central equation, you want to write a Green's function for it. Correct? In homogeneous equation, make it homogeneous, write the Green's function, put a point source, solve it, Green's function, and you get the whole superposition principle out. Same idea. But now we have it set like that, but it can be written a little more better. This is a vector, right? So this is a vector differential equation. But earlier we always got a scalar, right? We wrote a Green's function for a scalar potential. Yeah, but we did write it for a vector potential, but mostly it was a scalar. Laplacian was a scalar, right? Here we have a vector differential equation, and let me emphasize that more. Let me write this as del cross. Instead of electric field, let me write that as 1. It's just a fancy way of writing it if you want, but it has insight. This is a matrix of partial derivatives, okay, dotted with electric field, or omega is equal to omega square over c square chi of r omega, and electric field r omega. The thing that's a matrix, that's a dyadic. So this is called a dyadic differential equation. And whenever I have a differential equation which is not homogeneous, we have found that constructing a Green's function helps. So we will construct what is called a Green's dyadic. So a Green's dyadic will be, do this for a point charge, right? Instead of having this electric field so on, put a point source there, and the point source would be, or before that, for various reasons, let me, it's probably not necessary, but that is how it is there in the notes as it sits today. And so let me do this. Let me change this a bit. I multiplied by omega over square over c square. Same idea. But then this is gone, right? So it's chi, and that's e. And my Green's function now, this is the Green's dyadic. This shows up in your homework. I think all your homework is based on this equation.
I think it's C2 over omega 2.
Say that again?
The last line. I think it's C squared over.
Oh, yes. Thank you. Yeah, because I'm inverting it. Good point. Okay. So that will be c squared over omega squared. So 1 minus 1, and we put a source at r prime, and this will be a source, a point source, that's delta function, correct? Replace the right hand side for delta function, that's our Green's function, except that the left hand side, that's a dyadic, that's also a dyadic because there's a 1. So overall this is a dyadic, so right hand side has to be a dyadic, so I need a 1. So it's a little more than a Green's function, it's a Green's dyadic. Okay, so there are 9 partial differential equations in it. Right, is that clear? Can you imagine that? Like typically we have 1 partial differential equation which is not homogeneous, that is a delta function. Now there are 9 of them. 3 of them have a delta function. 6 of them do not have a delta function, which is 0. Okay, with me?
Okay.
Yes, right?
Yeah, so this whole thing, so it all equals like a big 3x3 matrix, which
So this is on the right side is equal to delta cube here, delta cube here, delta cube here, 0, 0, 0, 0, 0, 0.
okay.
Three of the out of 9 differential equations, 6 of them are homogeneous and only 3 of them are inhomogeneous in a sense, and that point source is contributing on that.
And the non-homogeneous forms in the diagonal part of the matrix.
Correct.
Okay.
Correct. And the idea is that, of course, the 1, when I multiply it with anything, I can generate the whole matrix by putting in whatever I want. Once I know it for 1, I can construct the whole matrix out of it.
Okay. Once you know one of the terms.
Correct. Once I know, basically, if I know, like it is like saying, how do you say this? If I multiply this with any source, so a source is this piece here, right? If I multiply that with on the left side and do that with the right side, I get my electric field. Like maybe I should.
Okay.
Or here itself, I can say this, like if you have a Green's function, L times a Green's function could be F is equal to G. Not call it G, maybe H. And instead, what you do is you try to do L times G is equal to 1, correct?
Okay.
Which means, so this is the idea of Green's function I'm going to write. So this is an operator, differential operator. This is what I'm looking for, the function F. That's my source or inhomogeneous part of the Green's function.
Okay.
Instead of this equation, I say that I construct an abstract equation where L times G is equal to 1. 1 here means delta function. It's a symbolic way of writing that. Okay. This immediately implies, in a sense, that L or G is equal to L inverse. Right? Just operate it on L inverse, then you have L inverse there, right?
Yeah.
L inverse has this meaning that it is the inverse of a differential operator. It's a symbolic way of saying that when you have a differential equation, what's the inverse of that differential operator? Think of it symbolically instead of really looking at this. But once that is the case, I'm interested in F. F is equal to L inverse of H, which is G times H. So once I have a Green's function, I immediately have the solution in terms of the source. Of course, this is an integral, but now in the matrix form, this is a matrix multiplying that source. So here, if I know this gamma, I have to multiply this to that, and I'll get my electric field. Once I find my Green's dyadic, if I multiply this to that, I get my electric field. G multiplied with H gives me my F.
Okay.
Right. Gamma naught multiplied with this gives me my electric field. Only catch being here that if you notice that this is a little complicated equation in the sense that electric field is there on both sides. Right. So that's called an integral equation, but we will in that radiation zone, we will have an approximation that will let us proceed. In the actual optics, that's not necessarily true. And so it gets a little more involved, or a little more tedious, I should say. Okay, if you were doing actual optics in here, that'll be the difference. That's what makes it simpler. Electromagnetic scattering is simpler than the standard optics. With me?
Yep.
Okay.
Yep.
So proceed further. And maybe we can do this in a significantly simpler way. Yeah, in your homework, you did this in a more elaborate way, but I'm going to take a shortcut. Okay. Now, shortcut is that, first of all, I of course expand this out, c squared over omega squared. And this is a cross and a cross, which is nothing but radian. So that's a back, right? Back cap. So this times this started with this. I have to make sure that everything operates on the right. But the gradient dotted with 1 is the gradient itself. So this is the dyadic piece that comes with the first piece. And then the second one is c squared over omega squared. That's what is the independent one. These two gets dotted. That's del squared. And there is a dyadic, which is 1. Minus of 1. Dotted with gamma naught is equal to 1. Okay. So that's your equation for your Green's dyadic. And in your homework, you pretty much begin from here. So your homework starts from this equation here, and you do these manipulations, and you have to do this in the radiation zone, which is pretty much maybe what I will also do. We'll see whether I want to make the simplification or not. So let me rewrite this equation and proceed. And I have how much? 10 more minutes. I should not take too long. Otherwise, I'll stop. Yeah, let me do a little bit more so that it helps you with the homework. And I promise that I'll try to stop in 5 or 10 minutes. So again, we have an equation. Maybe construct the problem at least. So this is del cross 1 minus 1 electric field. If you're interested in the electric field in the radiation zone, which is given in terms of chi of the source. And we have constructed a dyadic equation, which I'm going to, since probably you have the multiplying out by c squared omega squared again. So this is del minus omega squared over c squared. Oh, what did I do? No, this was having that. So that's a del squared and minus omega squared over c squared. Let me write that as a plus, and there's a 1 dotted with gamma naught is equal to, since I multiplied by omega squared, it shows up on the right side too. With me? So that's what we are interested in solving for. Instead, I construct a differential equation. And remember, this is a familiar equation, right? That's your old Green's function. We know the solution for this. So remember that. So remember, recall that L squared plus omega squared over c squared. That's your wave equation in the frequency domain, right? Omega is time derivative, right? So that's your wave equation. And if you write this as r minus r prime, this is scalar equation. This is a dyadic equation. So this piece shows up in that. Is equal to delta function. And what is G naught? So this implies what is that equal to? If omega was equal to 0, that's static. Omega means derivative. No, statics means omega equal to 0. That's your electric potential due to a point charge. Correct? How does it change if I'm not in statics, if I'm in dynamics, if things are moving, but now I'm in frequency domain? That's the part.
So now you just have a exponential term.
Very
the-
good. Exponential term, and that's a exponential of omega over c. It's a frequency dependent term. Very good. Right. So if you're in electrostatics, omega is 0, no derivative, no change. So that's 1. If you are having dynamics, there is frequency dependence, there is color dependence. If you want, if you're thinking in terms of optics, the color dependence comes because you're in dynamics in a sense. That's your Green's function for this. This is how they worked with before Maxwell, right? Whenever Fresnel worked on it, whenever Young worked on it, Fraunhofer, they all worked in this Green's function. But now we are making this elaboration where you're having all the modes available.
Now we just derived it. Okay.
Starting from Maxwell's, correct. We see why this equation shows up. They will put it, 200 years back when Maxwell was not there, we will just postulate that there is this equation, which is a wave equation, and proceed and get the solution. And the wave equation is mainly for a scalar quantity there. Okay. Okay. But this is, I have only shown you that, oh, there is this piece in between in here. But idea is that once I know this equation, I can get the dyadic equation in terms of this. But that I have to do in a few more steps. That's what we will do on Thursday, and then do it for a simple example, right? Once I have this Green's dyadic, I will get this electric field, and it will turn out the solution is very straightforward. In fact, so straightforward that in the radiation zone, the Fourier transform of this pretty much algebraically, there is not even an integration, algebraically will give you the electric field. Just give me chi, and we will do it for one piece. There is only one atom in the atmosphere. What is the scattering due to one atom? We will do that in a very simple scenario. And that is the Rayleigh scattering. That's why the sky is blue, right? We will get that effect in a very simple terms. So we'll get the electric field, and then we have to square it to get the intensity. So at this point, I'll stop. Hopefully I can finish all this on Thursday. Okay. Thank you for coming up at this time. This was nice. We had a class. I can say that I had a class at 9 o'clock with a full attendance, right? It's cool.
Yeah, it is.
Like COVID times all over again.
Yeah,
Yeah.
that's true. But this is out of interest, right? We were, instead of canceling, we try to. So some of the positive things we have captured from COVID. Yeah, we surely don't want to do this every class. No.
No.
Yeah.
Maybe once
Yeah.
in a while.
Yes, exactly. Yeah. I think the drawback here is that you lose visibility of the board, right? When you're in the classroom, you can look back at this. And the blackboards are one or two. And yeah, I mean, it's always good to have three things in the same.
Being able to see the whole thing all at once. That's
And I
cool.
can always hide. I can go out of the camera whenever I want to avoid the students, and students can avoid me by switching off the camera and all that. Yeah. So,
Is it about me and Aryan?
yeah. So it's that freedom is always there, but yeah, it's okay. Yeah. Some advantages. Yeah.
One person never turned on their webcam though.
One
Actually, my
person.
camera doesn't work properly, so
Rip.
it's broken.
Wanted to see your beautiful face.
You can see it tomorrow.
See,
Okay,
mush
thank you.
slides.
Is there a specific time we have to be at the?
No, it is available. I mean, it is open from 11 to 2. You can just come up anytime and leave at any time. Stay the whole time if you want. There is a mathematics professor from the Northeast. I don't remember exactly from which university. He's visiting Philip Feinsilver. He shows up in the potpourri seminar. So he's visiting our university. So I invited him also. So he will be there. So he works on pattern recognitions in the brain. So pretty, he once gave a talk in potpourri seminar. So it was kind of nice. So it'll be nice to talk to him. So we'll have a new.
If my dad is available, would you like me to invite him too?
Yes, please. That will be cool. Yeah. I will write an email. Yeah. Okay. You please invite him. That will be, thank you very much.
Yeah, I'll ask him if he's free or not.
Yeah. I will also send him if he feels anything uncomfortable. I was thinking of sending the email to Urek, John, and your dad and Puneet, but it's just my laziness, I suppose, or just procrastinating.
Right.
Yeah. Yeah. Okay. But thank you. Yeah, please do that. That'll be nice. Yeah. Okay. And you guys all will be there, I suppose. Yeah. Thank you. So for making this happen. Yeah.
Thank you.
Yeah,
Thank you.
thank you.
See y'all tomorrow.
Yep.
Yep.
See you.
See y'all tomorrow.
Mhm. Please.